Hi, everyone. Welcome back to day 2 of MIT Intro to Deep Learning. Thank you all for coming back for day number 2. Hope everyone enjoyed day 1. Today, we're going to be talking about one of my personal favorite topics in this entire course, which is how we're going to give computers the ability to have an ability that many of us have, which is the ability of sight and the ability to sense vision. So some background, first of all. So what is vision? Vision is one of the most important human senses that we all have. It allows us to do everything from detect and interpret human emotion and facial expressions, to navigate the world, to manipulate objects and manipulate our world around us. And today, what we're going to do in the class today is just understand fundamentally how we can give computers this exact same sense as well. The ability to understand what is in the physical world around it just from raw visual inputs. And I like to think of this very super simple definition of this ability just by this quote right here. This is the ability to know what is where by looking. And today's class will basically be focused on what we look at will be images. But in general, this is the broad sense of ability that we'll be focusing on. But vision is actually so much more than just understanding what is where, but it's also understanding a sense of planning as well, right? It's not a static sense only. But when I show you this image here, for instance, right, what you see is first you see the static things. You see the things like the cars on the side of the road. You see the people. But then, most importantly, you start to, as you look closer at this image, immediately what you'll feel yourself doing is also getting a sense of dynamics as well. Not only understanding what is where, but also how things are moving. You understand that even though these two cars are on the road, one of them probably is completely static, right? The white van on the left is probably completely static because it's parked on the side of the road. And even though these are both cars, you can detect them as cars, they are perceived very differently, right, when we look at this image. Same as these people on the side of the side of the road versus these people actually actively moving, right? And vision is actually all about not just understanding what these things are in this image, but actually understanding and interpreting the image holistically in terms of how things are moving, how things are changing temporally as well. And it accounts for all of these details in the scene. We take this for granted, right? When we look at all these things, even minor things like the traffic lights in the background, right? Very, very minor details that define, like the movement of even these future cars, right? We can infer a lot of things about this image the closer we look at them. And deep learning is really starting to bring about a huge revolution in computer vision algorithms and their applications. This is changing everything from robotics, manipulation, autonomy, to mobile computing. Everyone in your pockets, you have a lot of computer vision models running on these embedded hardwares. Biology, healthcare, right? Making sure that we can detect things the way that humans detect things from live or from raw imagery and raw medical imagery, to autonomous driving and accessibility applications as well. The real theme that you'll see throughout this class is how pervasive these algorithms, especially today's lectures, are going to be focused on the pervasiveness of these computer vision algorithms because they are truly everywhere. The one example that you'll get some exposure with in today's lab is going to be on facial detection, right? This is one of the original computer vision applications that was extremely impactful in the community. It just basically allows us to detect not just if there is a face there, but also features about the face, understanding micro emotions about the face that are extremely hard to detect and extremely hard to interpret. And of course, we've all heard a lot of buzz and a lot of hype around self-driving cars. This is a classic computer vision problem, right? What we're doing here is taking as input imagery. You can actually see the image that comes in on the bottom right-hand side of this video. Right, this is the raw camera image that's coming into the network, and this is an end-to-end network. This is a single model. This is very different, actually, than how most autonomous cars operate. It's a pipeline of mini models and predefined maps. Actually, this was work that we did here at MIT, where we created an autonomous vehicle. It's actually located in the garage of this building. to drive fully autonomously on brand new, never seen before roads, purely from visual input data. And of course, we already have talked about this a little bit, but we'll see some applications of what you'll learn about today in biology, healthcare, medicine, and so on. So I'd like to now start to dive into some of the technical basis of today's class. And I'll just preface all of this by saying that all of the amazing things that I showed in the previous slide, that today's class will be one of the classes where we'll be training these computer vision algorithms to do are going to a lot of times be tasks that we as humans take for granted. We do these things without even thinking about them, and we do them with such ease. And I think the question that will really boil down to today's lecture is how we can take something that all of us take so for granted and distill that also into computers as well. So in order to understand this, first we're just going to start with the most simple case, which is understanding just how a computer can process an image, right? Not even process it, but let's say even just represent an image. Well, to a computer, images are just numbers, right? Actually, images are a lot easier than language because images are already represented as an array or a list, a two-dimensional list of numbers. So if we had, for example, this image of Abraham Lincoln that you can see on this slide here, it's just made up of pixels, right? What is a pixel? A pixel is a single number, and since this is a grayscale image, every pixel is going to be represented by just one number. If this was a color image, every pixel would be represented by 3 numbers. It's a composition of red, green, and blue values instead of just a single gray intensity value. So we can represent this image nothing more than a two-dimensional array of numbers, right? One number for every pixel in this image, and this answers our first question of how a computer can see an image. So if we have, like I said, a color image, this is going to not be a two-dimensional array, but rather a three-dimensional array. It will be 2 dimensions by a third dimension, which is going to be this color axis, which will always be of length 3 for most images. And this is how we'll proceed for the rest of the class today. This is how we'll represent our images. And there are 2 types of common machine learning or deep learning tasks that we'll be focusing on, actually throughout this entire course, but especially for the purpose of today. And this is going to be the tasks of regression and the tasks of classification. So let's start with both of these tasks. So number 1 for regression, what is regression? Regression allows us to output a continuous value in our system, right? And classification, on the other hand, allows us to output a class label. So for example, the image that you see here could be mapped into a classification problem. Let's say we want to detect which US president is this image coming from, and the answer can be one of k or n different classes, right? These are discrete classes, and you can be one of those n classes. So in order to correctly classify images, like you see on the left-hand side, what does our model need to be able to do? Or what do we need to be able to do in order to do this ourselves as humans? Well, what we need to understand, well, what is unique about every one of those classes on the right? What is unique about a picture of Abraham Lincoln that makes it different than a picture of George Washington, right? If we understand those unique features, again, then those are the things that we can look for on the image on the left. But the first step is actually we need to extract, right, and define what are we looking for in each of those different classes, right? And that's this task of feature detection, right? Feature detection means nothing more than understanding what makes up one class different than another class, right? So another way to think about this is high level. Imagine classification is just done by a 2-step process. Number 1, defining what you're detecting in your images, and then detecting those things. And if you detect enough of them, then you classify it as that object. So for example, let's say for detecting an image of a face, you may look for features like eyes, noses, and ears. If you detect enough of those in an image, then you can have some confidence that you're probably looking at a face. On the other hand, things like houses are defined by features of doors, windows, and steps, right? If you look for those things in images, you can have some confidence that you have identified that if you successfully find them. So if you're building an image classifier, it really boils down to nothing more than this, right? You want to first define your features, know what you're looking for, and then you look for those things, and if you find them, then you can successfully classify your image. Now, this is easier said than done, right? Because one way to solve this problem of knowing what you want to detect, this is a big problem, right? Because knowing that you want to detect, let's say, a face by looking for eyes, now how do you detect eyes, right? It's a recursive problem. Now you have the same problem for detecting eyes that you had for detecting faces, and it's a hierarchical problem. And beyond that, it's also a problem where there are so many different variations and so many different adaptations. So you can imagine that faces look completely different depending on your viewpoint. It depends on your scale. It depends on your occlusions and things that are on different lighting and illuminations and so on. There's so many different variations of a single image in the pixel space, right? Even that same object taken with two different cameras can appear very, very differently. And this is why computer vision is so difficult for computers, even though we take it all for granted. So our classification algorithms, our models that we build in this class, they have to be able to be invariant to all of these different changes and all of these different modifications in our feature space, in the things that we're looking for in our image, in order to build a very robust pipeline. If we don't have that level of adaptability or invariance to these features, then we will not be able to be very robust in our detection. So it all really actually boils down to this last bullet here, right? So the detection of these features in order to classify is usually where machine learning breaks down and deep learning kicks in, right? So the machine learning world makes it very, very difficult to detect these features because defining the features in machine learning is a human process. Whereas in deep learning, we're going to say, okay, we're going to define these features using data. Now, what does that look like? Using a neural network, we can actually start to say, okay, instead of me defining as a human, saying that I want to detect faces by looking for ears and eyes and noses, and then defining recursively one more step, how would I find an ear? I would look for like vertical lines followed by like a circle underneath the line, something like this. I'm not going to define any of that as a human. I'm going to show my image, or show my model, a lot of images of faces, and it should be able to extract what is unique about all of these images of faces to help me disentangle all of those images of faces from pictures of cars, let's say, for example. What are the unique features, the unique styles of pixels that really differentiate these two things? And let's do that in a hierarchical fashion. The hierarchy here comes from the layers in my model. So the depth of my model curates hierarchy. And every layer of depth that is composed on top of each other allows us to inject yet another layer of complexity or expressivity, like we saw yesterday, right? Now, neural networks, all they do is allow us to learn this hierarchy implicitly as opposed to explicit definition instead of by constructing them manually by humans. So in lecture 1, we learned about how we could use fully connected networks to do this type of task, actually, right? This shouldn't sound so new so far, because what we've been talking about is simply just a composition of a multi-layer network where every layer is composed from the outputs of the prior layer, and every neuron in every given layer is going to be simply just connected to every input in that prior layer. So let's say we wanted to use what we learned from lecture 1 in this problem definition of what we're seeing right now with computer vision. How could we do this? Let's actually try it out. So in our case right now, unlike lecture 1, now we have a two-dimensional input. Previously in lecture 1, we just had one-dimensional inputs of features coming in to our model, but now we have 2 dimensions because we have an image. So let's feed that two-dimensional input into our fully connected network. What would this look like? So already, we come to a problem, right? Because what we have to do here is we have to flatten our image, our two-dimensional image, into a one-dimensional input, because all our fully connected networks can handle are one-dimensional inputs. That's what we learned about in lecture 1. So the only way to use a fully connected network for an image processing task would be to conform the images into a shape that these fully connected networks are capable of processing. Now, automatically, hopefully everyone in the audience, you can all understand and appreciate that absolutely 100% of the spatial information that was previously stored in this like very rich data type of an image is now completely gone. We've destroyed 100% of that spatial information by flattening it. And additionally, we also have a lot of parameters in this model because every single pixel in my input layer is going to be connected to every single neuron in my hidden layer, and that's only one layer, and then you have that depth-wise many, many times. So what we have is an extremely expensive model for actually a suboptimal solution where we've thrown out a lot of very valuable spatial information. So instead, what we want to do here is ask this question on the bottom, right? We want to ask this question of how can we preserve and leverage all of this really, really rich and unique spatial information present in our data natively. This is just part of the data, just to inform our network architecture. We don't want to throw all of this out for no reason. We want to leverage it and amplify our capabilities with it. So to do this, let's actually represent our two-dimensional image as its true form, right? Let's represent it as a two-dimensional array of pixel values. And one way that we want to use now the spatial structure inherent in our input is just to connect the input pixels in patches to our neurons. So previously, we had connected everything to everything. But in reality, what we're going to change now is say, OK, we'll keep the two-dimensional structure, but we will only connect things in our input pixel space to output neurons that are locally connected to each other in a patchwise fashion. So for example, this one neuron here will only see inputs from a local connectivity structure of patches of pixels from this patch here on the left. Likewise, this is actually repeated across the entire image. This one patch that you see on this top left-hand corner will give rise to this one output neuron, but the very next output neuron right next to it will be defined or guided by the next patch shifted one layer over. So everything is not connected to everything now. There is still a lot of overlap in information because you'll see that this neuron does share a lot of input pixels with this neuron, right? There is overlap there, but there's not complete, fully connectedness of the entire model, and we have successfully preserved a lot of spatial information. We have, enforced, basically by definition, that the neurons close to each other in the output layer will be derived from pixels that are close to each other in the input layer, right? And this is how we preserve spatial information. Now, in practice, what we just talked about is nothing more than an operation, a mathematical operation called a convolution. So what is a convolution? Let's first actually think of this at a high level. And suppose we have what's here represented as a 4x4 filter. I'll use that word now. So a filter is just, you can see this red box. That's going to be, I'm going to call that a filter. This is going to be consisting of 16, so 4x4 pixel weights, right? So you'll have the 4x4 pixels that come from the image. You will also have 4x4 weights that are coming from the filter. And then this thing will slide over my image step by step and apply the same operation that we saw in lecture 1, right? Element-wise multiplication, add a bias, apply a nonlinearity, right? No difference here, except everything is not connected to everything. You'll only do this on the filter level, right? Not for everything, but just for these 4x4 filters as you move across the image. And we're going to then just shift our filter. After every time that we do this operation, we'll shift it over and over and over again, let's say by 1 pixel or 2 pixels over, so that we can scan across the entire image. So probably you're already wondering, right, the next layer of complexity on top of this would be to really understand how the convolution operation actually allows us to extract these features. So far, I've only defined how the convolution operation works, but how is it allowing us to define what we started this lecture talking about is we want to define the things that we should look for in our image, and how does the convolution operation allow us to extract that information? So let's make this concrete by just walking through a couple examples. So suppose we want to classify or detect x's from a set of black and white pixels. So these are just images. They're two-dimensional arrays of numbers. In this case, they're not going to be gray. They will only be black and white. So everything must be either a +1 or a -1. And I want to build a model that can determine, does the left side equal the right side, right? So I have some examples of x's, and I see this new example on the right that is a bit of a skewed, rotated x. It's not a perfect x, so I cannot simply just compare the pixels on top of each other. I have to detect them more intelligently, right? So what we want to do is actually classify things on the right, if they are x's or not, even if they are shifted, they're scaled, they're shrunk, rotated, deformed, whatever the case may be. We want to be able to still have a very reliable detection. So let's think about this. So how can we do this using the same principles that we just saw? We can do this by having our model compare the x's not globally, but what if we did it on patch-wise? So if we looked at, for example, the patches of key interest, the things that define an x. What defines an x? Actually, there's only a few things that define an x. There's the diagonals this way, the diagonals this way, and then a crossing between the two, right? So here you can see three features that we're looking for. We're looking for a diagonal going from left to right. We're looking for a diagonal going right to left, and we're looking for a crossing, right? And if we do this comparison patch-wise, actually you can see that even though these features, these things that we're detecting, they may be in different places. So the green diagonal is not in the exact same place, but it's very close, but we are able to detect those features, right? And if our model can find rough matches on the patch level, then again, we've successfully detected the things that define an x that allow us to confidently say, okay, this is probably an x at a global level as well, if I can find enough of these patterns. So each feature basically is nothing more than like a mini image, right? It's a miniature image. It's a small, again, two-dimensional array of numbers, no different than the big image as well. But what we're going to use what we're going to do is use these filters, these convolutional filters, to detect and to define those patches, right? So in this case, the patches or the filters, represent, like we saw, diagonal lines and crossings of lines. These are all of the important characteristics of what make up an X. But in practice, probably we're going to want to capture these features for any type of new X that come in, right? Not just for this one X. And they will be robust to those types of perturbations. So okay, so this is, again, this is no different than convolution, but I'm going to keep kind of hammering the point home and start to actually introduce some of the mathematical terminology as well, so that you can start to familiarize yourself and how that translates from the intuition that you've seen on the past few slides to the mathematics on the next few. So what does convolution do? So the operation that does exactly what we've seen illustratively in the past few slides is convolution. But what does it do? It preserves the spatial information that is present within the images by breaking the big image down into smaller sub-images and then searching for key pieces of information across those sub-images. And to do this, it does this by basically doing an element-wise multiplication between what it's looking for and the original image at every point along the image. So let's say it's looking for this diagonal going from left to right, right? So the filter is going to be the following 3x3 miniature image that you see on the top left. This is a three-dimensional matrix, a 3x3 matrix, a 2D matrix, but it's 3x3. And in this case, all of the entries here, or actually, excuse me, all of the entries are -1 except for the diagonal, which is +1. This is because we're looking for this diagonal line. And we element-wise multiply this filter, this is what we're looking for, we multiply it with every patch in the image. So we'll start right here. This is the actual true patch, right? We'll look right there. We element-wise multiply the patch on the top left with the patch of pixels coming right here. And what we get when we multiply every number on the top left with every number in this green box, we'll get another 3x3 matrix with everything inside of it equal to 1, because there's a perfect match between every pixel in the top left filter with every pixel in our bottom or our image patch. Okay. Now that we have this the result of our element-wise multiplication, we'll do exactly what we saw in lecture 1. We take the result of element-wise multiply, we add them all up, and we pass them through a nonlinearity, which we'll see soon. Let's consider one more example before moving on. So suppose we want to compute the convolution of this 5x5 image in green with this 3x3 filter. So to do this, we need to convert, or we need to cover the entirety of our image with this filter. So we can do this by sliding our filter not just one time like we saw on the previous slide, but across the entire image, step by step, in piece by piece. And then at each step, doing the same operation, element-wise multiplication and addition. So let's see what this looks like. Right, so first off, we start with the top left corner. We place that yellow filter on top of the top left corner of our image. We element-wise multiply that 3x3 patch with all of the pixels in that 3x3 location, and the entries of all of those things, and then we add up all the entries after the element-wise multiply, and we get the answer of 4. Okay, and we're going to put that at this neuron location. So this is the output of our top left neuron of the first layer of our network. Then we slide over, one step over, and we do this exact same process again. Now there's a little bit less of an overlap with this filter. So what we're going to see is that the output of this neuron right next to it is 3. And we can keep repeating this over and over and over again until we slide over the entire image and fill over the entire, all of the patches, right? And that's it, right? So now what we have done is we've defined an operation that can go entirely from the input image on the left, given an input image, and given a patch, or excuse me, given a filter in the middle, define what is the output layer on the far right. Yes?
What's your choice of filter? Because
Yep.
that will determine the whole.
Exactly.
So what?
Exactly. So far we haven't talked about this at all, right? So all we've said is we're defining an operation, given an image, given a filter, how to compute the output answer. And you're completely right that the next step is to say, okay, we want to learn those filters because the filters actually dictate how good of an output answer you get, right? That's actually the tunable knob that will dictate this entire process. So we'll get to that in the next part of the lecture. Yes, great question. And actually, to motivate this, I mean, there's a couple things that you can do. For a long time, people have hand-engineered these filters. You don't even have to learn them, right? So if you wanted to detect lines, actually, there's like very good filters. You don't need to learn them. It's like easy to design a filter that can detect edges, right? This is a filter that detects something going from, a very high brightness value to a very low brightness value. It's a type of derivative filter, right? And in fact, people for many years have hand-engineered filters to serve different types of purposes. Here you can see some examples of different filters. So given an input image on the left, you can see that these are hand-engineered filters for sharpening images, right? Hand-engineered filters for detecting edges or even stronger edge detection in the filters, right? If you look at these filters, you can actually interpret them meaningfully, right? The sharpening filter amplifies the center and then minimizes the edges, right? And it's when it slides over the patches, you get that sharpening effect. The edge filter is, again, a form of a derivative, right? Kind of the opposite effect. So simply by changing the weights of the filter, as the question implied, you change entirely the output of the next layer. So the filter has a lot of importance, and defining your filter can have a lot of impact on looking for the things that you really care about in your image. So hopefully now there's very clear understanding, not just like on how we can compute the output of your convolution, but the importance of preserving all of this spatial structure and maintaining this through the convolution operation. Now that we've gotten all of this about the convolution operation under our belts, I think now it's time for us to kind of transition and say, okay, how can we, yes, go ahead.
What does the overlap with the 0 means? Because with 1 and minus 1, it made sense, the multiplication, and then we get 1. Mm-hmm. But when we have 0 in the filter and 0 in the image, what does that comparison mean?
It's still a comparison, right? So if we're looking for 0 in the image and 0, so it would be 0 times 0. So it's like a null passive information that you're not looking for anything in this location, right? So a 0 in your filter is almost saying that it's a null piece of information in this detection, right? Okay, so let's transition now to say, okay, how can we understand not just what the convolution operation does, but how we can start to define the inputs of the convolution operation. We already saw, obviously, The input image is well defined, right? We give this as an input to the model, but what about the filters themselves? And to do this, we can zoom out a little bit and see where we're going to end up with the entire convolutional neural network. Let's consider a simple CNN. A CNN stands for a convolutional neural network designed for image classification. So the goal here is to learn these filters or these features. They're the same thing, same word, two words, just different, same meaning. We want to learn those features from image data. So given a bunch of images on the left-hand side, we want to learn what are the filters or the features that can disambiguate the different classes that can come out on the right-hand side. And there are three main operations to CNNs. We already saw one of them, right? So the first one is convolutions, right? Convolutions define this processing of patchwise operation, scanning across our images. The second, we also have hinted at already, it's the nonlinearities that come after each of our convolutions. And then finally, the third piece is going to be pooling, which is just a downsampling operation that allows us to grow our receptive field, right? Because if we're doing this thing patchwise over the image, we also need to have different layers of depth and like how big our patches are. So by downsampling the image, we're effectively upsampling our patches in the same way. So we can train our model on a set of images, and in training them, what we're going to do here is learn those filters, right? Now, we'll go into more depth on this, but when we define the model with this framework, all we're doing here is, via backpropagation, you define all the operations, you show the data, and then you can compute the optimal set of weights or the optimal set of filters that will optimally solve this task. And you do this through optimization. So let's go through each one of these operations just to break this down even further and see how this looks even more concretely. So let's dig even deeper into the convolution operation in the CNN. And as we saw before, each neuron in our hidden layer, so the output of the first layer of our model, this is just going to be computed with this weighted sum of our inputs with our filters. We apply a bias, we add up everything, and we apply our nonlinearity, right? Now, what's special here is really I want to highlight this point about the local connectivity. The local connectivity allows every neuron in the hidden layer on the right to only see this patch of input pixels on the left, right? That's really important because now we can really define this computation in math, right? Moving from all of the illustrations that we saw before, for a neuron in the hidden layer, its inputs are the neurons in the patches in the previous layer. So what does that look like? We can apply this matrix of weights. Also, we've been calling them filters or features. This is a 4x4 matrix in this case. To do this element-wise multiplication, we add the outputs, apply the bias, and apply our nonlinearity. Same story as before. But remember that our element-wise multiplication and addition is nothing more than convolution. This is literally just convolution that we talked about earlier. So this defines how neurons can operate in this forward pass, right? But within the convolutional layer, we don't do this for only one filter, right? Every layer does this for a whole set of filters. So you may say one layer is looking for a wide variety of different types of edges. It may learn to look for those filters in a huge variety of edges and then use that in the next layer in the detection of those many different types of edges. So what you'll see is actually in this slide, you're not outputting just one two-dimensional image of your filter output. You're outputting an entire volume. And the volume is derived from not just one filter, but now an entire depth-wise of filters. And again, this is just one layer of your convolutional neural network. So one layer in your network takes as input, again, a volume, but let's just call it an image on the first layer. It takes as input your image, and it detects n different filters across that image. It gives you back a new volume, which is that image convolved with those n filters. Now, the next step, after we have that volume, as we saw before, is we compute or pass them all through our nonlinearity. This gives us our nonlinear capacity and our expressivity that we saw about and we care about in the first two lectures. We've been talking about this. Now, a common application for images in particular is to use nonlinearities like the ReLU activation, the rectified linear unit that you can see here. Why may you want to do this is because the ReLU activation is basically a form of a thresholding function, right? It gets rid of all negative values, it squashes all negatives to 0, and it keeps everything positive as what it is. So you can kind of think of this as a very intuitive meaning in computer vision as a thresholding function, right? So you just want to get rid of everything and squash it all to be positive. Yes.
So the convolution step is to prepare the input. Is that correct? But you don't do any further convolutions. That box that you showed last time.
Yes. So the convolutional step is to detect features within the input, and then the nonlinearities is to increase the expressivity of those detections, right? To make them nonlinear detections. Now, you don't do any more convolutions in that first step, but you do have a deep network with many of those layers. So each layer does one convolutional operation, but then you stack them sequentially in depth-wise.
Why would you need to do further convolutions? If I just think of the previous, yesterday's lecture, I think what I understand is that you prepare the input by these filters. Then you have your input parameters. Am I missing something? Probably.
Yes. So
Why would you need to do further convolutions to scale down? I think what I
I see.
convolutions will scale down.
No. So actually, convolutions will not necessarily change the spatial resolution of the image at all, right? So as you can see here, right? So, I mean, it shouldn't need to change the spatial resolution. You can implement convolution in different ways, right? But let's say in the example here, right? If you pass over your filter, typically filters are much smaller than the size of your image, right? So you'll have a output size resolution that is roughly the same size as your input image. So spatial resolution does not change as a function of convolution. There's different ways to implement it where that may not be true, and we don't have to get into that now, but generally, let's say it like this. You change the spatial resolution to do this, like, let's say, multi-scale operation of detection of features. So you do it one time, and you're detecting features at one scale. Then you downscale this volume, and then you repeat it again. The next time you repeat it, you're now detecting features at a bigger scale because you've now downscaled your volume, right? And this repeated process is what allows you to detect features not just at the original size, but repeatedly across many sizes, right? And to also have those features compound on each other, right? You may want your features to be hierarchical, so you want to say, okay, I don't want to also only detect edges, very basic features, but I want to compose, okay, this edge combined with this edge. That can only be possible if I take it from the output of the second convolution, not the first convolution, because you want compositions of detections, not just original detections. Yes?
So during this operation of multiple steps, do you sometimes follow and then use a hidden filter or always the same filter?
So filters will always be different because filters are learned. They're not defined by human, right? So within a single layer and across layers, filters will, always be different because they are going to be randomly initialized and then optimized by data. So you'll always have a set of filters when everything is said and done. You'll have a set of filters that will have very little overlap with each other throughout your network, unless you have a huge network and you must have overlap, basically.
So before it lies the case, during the process, do you know what kind of filter you apply? Can you detect that kind of?
Exactly. Yes. We'll see some examples. So actually, let me go forward a couple slides because this will become much more apparent very soon. Now, we touched on this already, but why do we do something after convolutions? We do this pooling operation. Pooling is nothing more than downscaling our dimensionality. So after every convolution, we get an output set of features that are detected. We downscale those features, and then we repeat the convolution again. Because the next time we do the convolution, we will have now a larger receptive field because our input image is now smaller. A common technique here to do this downpooling is something called max pooling. This is basically just saying, okay, you'll take a patch on the left-hand side and you'll pick the maximum value from that patch and you'll put it in this 2x2. And from a 2x2, you'll put it in a 1x1 single maximum value. There's many ways to do pooling and dimensionality reduction. Max pooling is only one way. You can think of ways that are less, for example, harsh on derivatives. Max pooling is actually quite harsh because derivatives don't pass through 3/4 of the pixels. By doing it like this, you'll only have a derivative through the 1 pixel that activates the maximum. Imagine, for example, if you did mean pooling instead, you would have stable gradients throughout the entire patch instead. So you can think of clever ways to do other forms of down pooling as well. It's a very open point. Okay, but getting back to this point of how do we interpret and how do we see the filters that are being learned, actually you can, as the model trains or after the model trains also, you can visualize those filters, right? So you can actually look at what the convolution neural network, what the convolutional layers are optimizing themselves to detect in this image. So here's an example of a convolutional neural network learning to detect faces. And you see basically 3 different levels of activations of filters that are being activated by this network. In the beginning, it's looking for basically these edges, like changes in intensity value with different directions. As you move up in the model, you start to combine those filters and those features together that are being extracted hierarchically, and you start to see actually facial features start to emerge, things like eyes, noses, and ears, like we were talking about before. And then you move up even more than this, and you start to see full structures start to emerge, right? Now, with CNNs, the key point here that are different than machine learning is that we didn't define any of these filters ourselves. We've learned these filters by showing the model a lot of data and asking the model, hey, what are the filters that would be best for you to use in order to get your accuracy of detecting faces as high as possible, right? We only penalize it when it's not able to detect faces, and we say, hey, keep changing your filters until you're able to detect faces better, and this is what it comes up with. These are the filters of things that it's learned to detect in order to do this task most accurately. So roughly, actually now this whole process is just broken down into 2 parts, right? Part number 1 is extracting these features using those learned filters, and part number 2 is going to be using those features to do some form of detection, right? In this case, we're talking about facial detection, right? So there are these 2 pieces, right? How can we take the features that are learned from phase 1 on the model to inform our classification phase, right? We can do this with a function called a softmax function. What is a softmax function? This is just a function that takes our n outputs at the last layer and squashes them to have a sum to 1. Why do we do this? Because we're caring about classification in this case. And if you want to classify something, you have to have a probability distribution. What is a probability distribution? You have to have mass that sums to 1. Okay, so now let's put all of this together in code to build our first end-to-end convolutional neural network. We can start by defining those 2 parts of the network that we saw in the previous slide. First part is going to be the feature extraction part. This is the part with all of the filters. This is going to have 32 feature maps, you can see right here. So the first volume that comes out of this first layer will have a volume, a depth of 32 features, corresponding to 32 filters that have been learned in this first layer. We will downpool the spatial information, and then we'll pass it onto yet another convolutional layer that takes those 32 features and learns another 64 features on top of them at a smaller dimension. We're going to then flatten all of this. Now we can remove our spatial information. We go into a 1-dimensional space because now we're actually wanting to make a 1-dimensional prediction on the classification. So we flatten everything because we've already learned our spatial information, and then we project to a softmax function that allows us to predict our probability distribution and allows us to output our final, let's say, 10 classes, right? If we're trying to predict numbers, we would have 0 to 9 different classes. That's 10 total classes. In PyTorch, you'll see a very similar version of this code, right? Almost identically mirroring what you saw before, right? Again, we define the convolutional layers, 32 followed by 64 features, a flattening operation that allows us to enter the 1-dimensional space and then pass into our final output dimensionality. Yes?
Could you say a few words about how you choose that there's 3, the patch is the size 3, and there's going to be 32 feature maps and 3 layers. It seems to me that might be more of an art than a science.
Yes, yeah, it's an art, but it's also, it can be guided by a lot of intuition, I guess. So some intuition that I'll provide is that typically you want your features, especially depending on the task, you want to start out quite small, but you want to preserve, you want to upsample spatial information as you go deeper into the model. So you want to make sure that you understand, first of all, what are the, based on your image, based on your data set, you want to understand what, looking at this as a human, what are the scale of the features that this model should be looking at to detect in the beginning and at the end? And those will define basically those two resolutions, right? If you're saying, okay, this is a massive image that's, let's say, 2,000 by 2,000 pixels wide, starting with, 3 by 3 will be too small, right? Probably for most images, right? It doesn't make sense to look at that small scale if your image is 2,000 pixels wide. But then there could be other applications, it's very small, and even 3 by 3 is already like a significant resolution in that image, right? So it's very problem dependent as well. Yes? Yeah, sorry, go ahead.
If you train your in this case, faces all oriented in normal fashion, I'm assuming that this method wouldn't allow you to turn the face sideways and still classify it, or what?
Not if it wasn't trained on faces that were sideways. This is a great question. So the question was, you train it on upright faces and then you test it on faces that are turned sideways. And no, we would not expect it to do well in this case because it has learned to detect features of faces that were always upright. If it was shown faces of both orientations, then we would expect it to do this successfully, right? Because we would expect that then it should learn that faces can be in either orientation. So it should learn to pick out those features in both cases. Yes?
How would this approach work for deformable object? For example, if we have a gummy bear, or if we have a fluid simulation, like how is it applicable at all, or?
It's very problem dependent, but again, we'd want to make sure that we can learn from data, right? So even in these more dynamic cases, right, we'll see some examples later in the deck, right, of these types of situations as well. But really, we want to make sure that these are all learnable from data. Okay, I'll continue on just because we have a lot more to get through. So far we've talked about CNNs only for classification tasks, but in reality, this architecture extends far beyond classification as well. Remember this picture I showed you before? I think this is a really helpful picture because it decomposes all CNNs into two pieces, right? A feature extractor and what we previously saw was a classifier. But actually the second piece can be really anything. You could take a feature extractor and use it with an object detector, a classifier, a segmentation model, a probabilistic control model, a regressor model, or so on, right? So in this portion, we're actually gonna look at what are all of the different types of models that you can create just by keeping this left side static, use the same feature extractor, but now let's see if we change the right-hand side, how can we achieve a lot of very different things and different types of model that look very different, but in reality, they're actually not so different at all. So in the case of classification, we saw this already, right? That right-hand part of the network is nothing more than a flattening operation over all of our features, and then we classify over n different classes, right? So here, for example, you see an example of basically classifying binary, right? Diagnosis or not diagnosis. This is a paper that came out a few years ago that basically demonstrated that CNNs can outperform radiologists for these types of diagnosis tasks for mammogram images. Classification is an extension of, or classification, let me say it like this. Classification is a binary problem, typically, or a k-set problem. It doesn't have to be 2 classes, but it could be k classes. Let's go one layer deeper, right? So this is an image of a taxi. Classification would be me saying, okay, I input this image and I predict taxi, right? How about object detection? Object detection would be not just predicting the class taxi, but it would be predicting a couple more things. It would be predicting a location of that object, a class for that object, and an exact bounding box as well. So it's not just a location of the center of the object, it's a location of the entire bounding box of that object. And the neural network has to tell us for not just this one object, but actually for every object in this scene, where it is, and also the class of that object. So our model needs to be extremely flexible in order to do this type of task, because now it's not outputting just n sets of different outputs or k sets of classes. It will output, if the scene has only one taxi, it will output one bounding box. But on the other hand, if the image has many objects, right, it should be flexible enough to have many outputs as well, right? So potentially even these outputs could have different classes, obviously different locations, different different numbers and ordinals as well. So how can we accomplish something like this? This is very complicated because number one, those boxes that we saw, they can be anywhere in the image. They can be of any size, and they can be of any ordinality. You can have many of them, or you could have no boxes actually in your image. So let's consider a very naive way first, right? Let's take our image on the left-hand side, and let's start by placing one random box over the image, right? We'll just we'll pick a random box, we'll put it over that image, and we will take that one random box and we will pass it through a CNN that we trained before, right? The feature extractor, and then we'll use that feature extractor in the old way. We'll use it as a classification model. Even though we talked all of this stuff about making this very flexible, we'll just do this in the old way first. But we will do this repeatedly. We'll keep picking random boxes, and we'll say, okay, is there anything in this box? No? Okay, go to the next block. And we'll keep doing this over and over and over again for enough boxes in the image. We'll fill up our entire image with a bunch of classifications and simply discard the box if there was no class detected. Right. Now, there's a lot of problems with this, but the main one is that there's way too many inputs here. It would be way too computationally expensive, and even for any practical image, you would never completely have coverage over this image for all of the types of boxes as well. There's an exponential explosion of number of boxes with respect to resolution, so you can't simply do this type of naive method, but it gives us a good starting place. So instead of picking random boxes, what if we were a bit more intelligent and we used a heuristic method? So actually there's pretty simple heuristics that we could build that pick boxes around things that look like they have stuff happening in that part of the image, right? You don't have to know anything about the image, but just looking for like blobs in the image, you can create a pretty decent heuristic that just identifies, okay, here's a potentially interesting piece of the image. I'll draw a box around it and pass it through my classifier. But still, actually, this is still very slow because I need to draw a lot of boxes for this to work well. And we have to feed in each box independently to our classification model. So it's very brittle because now also we've completely disconnected these two parts of the problem. We talked also a lot about this end-to-end model that goes from feature detection to classification, but now I've broken that model. I've said, okay, I'm going to have a proposer, a box proposer model over here that will propose boxes for me, and I'll have another classification model which takes those boxes and processes them. But if ideally we want those two models to share information. In order to predict good boxes, it should know what it's looking for at the high level, right? So how can we solve this? This is one way that you'll see and hear a lot about. I'll present it very briefly so everyone is familiar with it. It's called a RCNN method, right? So this is a regional CNN, convolutional neural network method. What it attempts to do is actually learn those regions, those boxes. It attempts to learn it within the same network as the model that classifies those boxes. So what does this mean? This means that we can start from the bottom. We start from our original image, and we have this region proposal network. The region proposal network takes as input the image, and it proposes regions, right? It learns to extract features of where are high importance regions within the image. And this is used to define the boxes that I use for the classification model. So I take those regions, I draw boxes around them, and then I pass them through the same classifier using the same features that were learned to predict those regions. So now there's good alignment end-to-end in this entire process. This requires only a single forward pass to do this entire model now. So it's very efficient compared to the models that we saw before, and it's very accurate because it's actually sharing features along this process. Okay, so in classification, we saw that we went one step beyond we started classification, then we went to object detection, goes one step beyond classification. We're going to go one step even now beyond object detection to segmentation. So instead of just predicting boxes in the image, what if we predicted for every single pixel in our image a classification? So now, given an image on the left-hand side, we want to predict another image on the right-hand side with a classification value for every single pixel in that image. Right? So one example of this is just shown here. This is a semantic segmentation model. Semantic means that we're learning the semantics, right? The classes of every pixel in our RGB image on the left-hand side. So here you can see basically an image of a cow on the left-hand side being semantically segmented into a few different categories: grass, cow, looks like trees and sky in the background as well. So how is this done? The first part of this network on the left, this is the same feature extractor that you saw before. It's composed of convolutions, downpooling, and nonlinearities. The second half is no longer a classification model in the one-dimensional case, but now it keeps everything in 2 dimensions, but it upsample convolutions now. So instead of going convolution followed by downsampling, we do a convolution followed by upsampling. And again, we learn the output on the far right to be just a classification of all of this. So this is nothing more than another classification problem where we didn't downsample to 1 dimensions. We just kept everything in 2 dimensions, and we used upsampling instead of downsampling. Let's see one final example. So let's say we want to learn a neural network for autonomous navigation, like we saw in the beginning part of the class for self-driving cars. And let's specifically say we want to learn a model that can go from raw perception, camera data, and as well as noisy street view maps. Let's say like what you would get on your Google Maps on your phone, for instance. Right? These are like bird's eye view pictures of where the car is at this point in time, but they're just pictures, right? And you want to feed both of these into a neural network and allow the neural network to learn how to drive based on these 2 pieces of information. If you think about it, actually, this is all that humans need to drive as well, right? We only use 2 eyes, and we use Google Maps. If we go to a new city, we need some layer of navigation information to drive through that city. And what we want is we want to directly infer not just one steering wheel angle, where the steering wheel should be, but we want to infer a full probability distribution. Again, it's a form of a classification problem, but now we're not just predicting over k discrete classes. We're going to learn a continuous probability distribution because steering wheel angles are continuous. They can be anything from let's say like negative 180 degrees to positive 180 degrees. It's a continuous value. So this entire model can be trained using exactly the same techniques that we learned about today. We can pass through each of those images on the left-hand side through the same types of modules that we've learned about. These are convolutional layers, followed by nonlinearities, followed by downsampling. Right? All of that gives us features that come from each of those images at the output. We combine all of those features in 1 dimension, and then we use that to learn the control parameters of the vehicle. And then we regress on that with backpropagation. We learn the features and we learn the filters that are optimal for this type of task by watching a lot of driving data and learning, okay, what are the good features that I should learn in order to do this task successfully? Right, and in the end, the result here is that this is an autonomous car that has never driven through this road before. It can actually drive brand new roads, never seen before, without maps. This is something that's actually very different than how you'll see like Waymo cars. Google cars are quite different than this because they require to drive through a city once human driven before they can drive autonomously, right? Humans don't operate like this, right? We can be put in a brand new city for the first time and we can successfully drive in that city without ever seeing it before, right? And this type of a model is also able to exhibit that type of behavior. So the impact, I'll just conclude briefly, right? Because the impact of CNNs has been very wide-reaching beyond these examples that we've talked about today, but hopefully what you can appreciate is that in all of the examples, actually, they all come from these exact same fundamental techniques, right? It's convolutions, the operation itself, it's feature learning to learn those filters, and then some amount of some combination of either upsampling, downsampling to preserve or modulate spatial resolution. So I'd like to basically, summarize now all of this. So first, we considered, a lot of the origins of computer vision. We took some history back through how images are represented. They're represented as these two-dimensional arrays of values. We went one layer beyond that to say, okay, how could we learn from those two-dimensional arrays using convolutions to extract meaningful pieces of data and then formulate that into full networks, not just a single convolution operation. And then many applications with that backbone of convolutional layers, many applications that can be spun off very easily of different types of models from that point. Anything from classification to detection to segmentation and many others as well. I'll pause there and I'll transition to Ava, who will be talking about generative deep learning as well, which is actually how we can, which is a brand new thing that we haven't talked at all about in this class. It's not just how we can learn from data, but to learn from data to generate more data, right? It's a very different, it's not only a different type of model, but completely different paradigm than everything that we've seen so far in the class. So we'll take a couple minutes, we'll do a transition, and then we'll continue in probably 2 minutes. Thank you.